Good afternoon, everyone. Welcome back. It's probably right on stuff. Okay, you can start. Hi, maybe let's get started. It's already past 2. So welcome to the afternoon session. So this session is mainly about entanglement and in different perspectives. The first one is given by Xin Wang. He talks about the SDPs and the other tools for the optimization problem related to the characterization of entanglement. Okay, that's it.
Okay, thanks, Xiaodi. And good afternoon, everyone. Thank you for coming to this talk. My name is Xin Wang, and I'm a PhD student from the QSI at UTS. And I will give a talk about asymptotic entanglement manipulation. And this is a joint work with my supervisor, Renyao Duan. And as you know, entanglement theory is the resource theory of entanglement, where we use free operations such as local operations with classical communication. And entangled states are just a quantum state which cannot be created by local operations and classical communication. And motivated by entanglement is the key resource in quantum information theory. We study how to check. See. So we study how to detect, how to quantify, how to manipulate, and how to use entanglement. And in this talk, we mainly focus on the bipartite entanglement, and we'll study 2 fundamental processes in entanglement manipulation. The first one is the entanglement distillation. It is introduced by Bennett et al. In 1996, and the aim of this task is to extract standard 2x2 maximally entangled state from a given state by LCC. And it's some kind of, we hope to distill good entanglement from the given entanglement. And this is because the maximally entangled state is kind of a currency of entanglement theory. It is useful, and it can be used in superdense coding, teleportation, and many other quantum information processing tasks. The reverse task of this entanglement distillation is the entanglement dilution. It is about prepare a given state rho with the maximally entangled state by LCC. Corresponding to these 2 very fundamental entanglement process, there are 2 important entanglement measures with operational meaning. The first one is the distillable entanglement. It quantifies the optimal number of EPR pairs we can extract from the given state in a asymptotic setting. Mathematically, it is given by this equation. It maximizes the number R such that we can use LCC to transform the given state to the maximally entangled state approximately in the limit of n. And another one is known as the entanglement cost. It quantifies the minimum number of EPR pairs we need to prepare the given state in a asymptotic setting. And mathematically, it's given by this similar definition. And the remarkable result is that this quantity equals to the regularized entanglement of formation. It is proved by Hayden, Hordetsky, and Tahor in 2001. So a natural question is to ask whether this kind of asymptotic entanglement manipulation is reversible. That is, whether this entanglement cost and the distillable entanglement always coincides. And for pure state, Bennett et al. Shows that this kind of asymptotic manipulation is reversible. And both the distillable entanglement and the entanglement cost are given by the entropy of entanglement. However, for mixed states, this kind of reversibility does not hold anymore. It is proved by Vidal and Sirac. And an extremal case is the bound entangled state, whose distillable entanglement is 0. And Yang et al. Shows that for any bound entangled states, the entanglement cost is always positive. And so if we want a reversible theory of entanglement, we need to consider enlarge the set of operations. One candidate is the set of PPT operations, which are just quantum operations completely preserving the positivity of partial transpose. This kind of operation is strictly stronger than the separable operations, and clearly it is more larger than the LCC. So under the PPT operations, the distillable entanglement and the entanglement cost can be defined in a similar way. And we just replaced the LCC operations by PPT, and its PPT entanglement cost is also defined in this similar way. Since PPT operations are more powerful, so its distillable entanglement will become larger, and its entanglement cost will decrease. So the question now becomes, is the reversibility holds under PPT operations? And there are some evidence that is the class of anti-symmetric states of arbitrary dimension is such an example of reversibility under PPT operations. It is proved by Ordinate, Planio, and Eisert in 2003. And also another result that any NPT state is distillable under PPT operations also suggests the possibility of reversibility under PPT operations. And based on this, Ordinate, Planio, and Eisert introduced an open problem in 2003, that is whether the PPT operations are sufficient to ensure this reversibility. And it is also a problem listed at the website of Reinhard Wiener's group. This problem also asked for the smallest set of operations which ensure the reversibility. And in 2008, Brendel and Planio give a partial answer, and they show a remarkable result, that is, entanglement can be reversely transformed under asymptotically non-entangling operations. But the reversibility problem under PPT operations were still unknown. So based on this background, in this talk, we would like to study how to efficiently estimate the distillable entanglement as well as the entanglement cost. And also, we will try to study the reversibility problem under PPT operations. And we want to study whether the PPT entanglement cost is equal to the PPT distillable entanglement. And the outline talk is given here. We will first study the distillable entanglement and give improved upper bounds for it. And then we give efficiently computable lower bound for the entanglement cost. And finally, combine both these results, we will demonstrate the irreversibility under PPT operations. That is, we will find a state rho such that there is a gap between these two quantities. So let us begin with the distillable entanglement. how to evaluate the distillable entanglement is actually a formidable task, and it is only known for very limited cases. So we hope to find some easy to computable upper bound. One such upper bound is the log negativity introduced by Vidal and Wiener in 2002, and later Planio shows that this is a four-entanglement monotone. And this log negativity is another version of the negativity, and Reins, Vidal, and Wiener prove that this log negativity upper bounds the PPT distillable entanglement. And this quantity also has many other properties, as you will see later. So our first result is a better SDP upper bound on this distillable entanglement. The upper bound is given by this simple SDP. It's just, you can see more clearly from the dual here. It minimizes the log negativity over all the operators x, which x is larger than a given state. And this SDP has many nice properties. For example, it is additive on the tensor product, and it upper bounds the PPT distillable entanglement. Moreover, it is positive if and only if the state is PPT distillable, and also it is non-increasing in average under the PPT operations, which means it is four-entanglement monotone. And finally, it improves the log negativity. And the inequality is strict in general. To see this, we only need to refer the dual SDP. Since x equals to rho is a feasible solution, then the optimal value of this SDP is always smaller than or equal to the log negativity. And we also note that the log negativity also has property 1 to 4. And there are also other forms of upper bound on distillable entanglement. And there are two upper bounds in the form of relative entropy. Relative entropy of entanglement with respect to PPT state was introduced 20 years ago, and it minimized the relative entropy distance from the given state to the set of PPT states. It gives upper bound of the distillable entanglement. And we also call the asymptotic relative entropy of entanglement as this regularized entropy of entanglement. And in this talk, we mostly concern this relative entropy of entanglement with respect to PPT states. The best known upper bound, to the best of my knowledge, is the Reins bound. The Reins bound was first introduced by Reins and later refined as this convex optimization problem by Ordinate et al. And since this Reins bound is the best known upper bound, there are two problems still open. First one is the conjecture made by Ordinate et al. In 2002. That is the conjecture that the Reins bound is always additive. And another open problem is introduced by Planio and Viermani in their nice review about entanglement measure. That is, they ask whether the asymptotic relative entropy of entanglement equals to the Reins bound. This is based on the evidence that these two quantities equals to each other for all the Wiener states and also orthogonally invariant states. And here our second result is that both answers to these open problems are negative. That is, we can find a two-qubit state rho such that the Reins bound is not additive, and also the asymptotic relative entropy of entanglement is strictly smaller than Reins bound. And we will briefly show the proof ideas here. The proof idea is simple. That is, if we cannot prove something, we go to find the counterexamples. So we start from the 2x2 state. And in the 2x2 case, we use a technique in Ranowski and Ihizaka's paper. That is, the Reins bound equals to the relative entropy of entanglement for any 2x2 state. And their paper also give the sufficient condition of the closed PPT state of a given state rho. So we construct the state rho and the closed PPT state sigma to ensure that the one-shot range bound here equals to the relative entropy between rho and sigma. The second step is to consider the two-copy case. So since the two-copy case is a little bit complicated, so we try an algorithm developed by Girard et al. Recently, and this algorithm helps us produce PPT state tau such that it gives an upper bound of the two-copy relative entropy of entanglement. And the next step is to consider these two relative entropies. And there is a strict gap between these two relative entropies. And the left hand of this relative entropy actually upper bounds the two-copy range bound, and the right hand of this inequality exactly gives the double of range bound. And then we obtain the non-additivity of range bound. And also, we can use this to show that the asymptotic relative entropy of entanglement in this case is strictly smaller than the range bound. And this is an example of semi-analytical and semi-numerical proof. The counterexample is actually a little bit complicated, and we try to simplify it but failed. This may probably because the nature is too complicated. But the things we can make sure is that this satisfies the sufficient condition, so we can make sure the one-copy range bound is exactly given by the relative entropy between these two states. And then we consider the two-copy case and calculate it and give the gap. Then we can show that the range bound is not additive. So with this, we have some applications. The first one is that then we need to consider the regularization of range bound. And the regularized range bound clearly will give a better upper bound of the PPT distillable entanglement. And we also mentioned that Hayashi already introduced this quantity in 2006, but at that time, the non-additivity was still open. So this also leads us to consider some new problems. That is, whether the asymptotic range bound equals to the asymptotic relative entropy of entanglement. This problem is important since these quantities just lies between the PPT distillable entanglement and the PPT entanglement cost. One day, Andreas Winter and my supervisor Ren Yao told me that if you can find a gap between these two quantities, then you can prove the PPT distillable entanglement is strictly smaller than PPT entanglement cost. And I was excited after learning it, and it just holds for 10 seconds since the tough thing is how to evaluate these two regularized quantities. And so we continue this line, and finally is our key result. That is, we can show find an entangled state rho such that there is a gap between these two regularized quantities, and this immediately will give us the reversibility under PPT operations. And this means that if you distill maximally entangled states from the given state rho, the number of maximally entangled states you distill is not enough to reproduce the given state. That is, there is a strict gap between these two quantities. So how to prove it? Our key contribution is to introduce an efficiently computable lower bound for the regularized relative entropy of entanglement. And the lower bound is given here. We suppose P is the projection over the support of the state, and the lower bound is given by minus log eta P, where eta P is the SDP given here. So the brief idea to prove this lower bound is given here. The first thing we need to do is to transform or relax the convex optimization problem to a semi-definite program. So we did some relaxing. The original problem is the distance between the given state rho and the set of PPT states. So we relaxed the target. We relax it to the distance between this state D, which contains the order states whose support contains in the support of rho, and we consider the distance between these two sets of states. And also did some further relaxing. We obtain a SDP lower bound here. And after completing the paper, we also found that this step can also be given by the mean relative entropy introduced by Data in 2009. And the next step is SDP is powerful, so we try to use this tool to further relax it. So we use the weak duality to relax it to this maximization problem. But however, we found that this quantity is still not additive. And we have exact examples of it. So we consider how can we further go with it. And so the idea here is let us try to make the constraints more symmetric. So we add two constraints. For the first constraint, we let the partial transpose of y larger than minus T1, where 1 is the identity. And also, we did the same thing for the second constraint. And obtain this lower bound, we call it E eta. And also, we using the strong duality of semi-definite program, and to prove that this quantity is finally additive under tensor product. This is a powerful lower bound since we can use it to lower bound the regularized relative entropy of entanglement since it is additive. So with this lower bound, we still need to consider which kind of example can show the irreversibility. If we do not have examples, we still do not prove it. So we consider the 3x3 anti-symmetric subspace. Since the rank 1 state is pure state and the rank 3 state has already been proved, so we choose the rank 2 state. And given here, combining the upper bounds and lower bounds we developed, we show that the asymptotic range bound as well as the distillable entanglement is given by this number. And at the same time, the entanglement cost is exactly given by 1. And there is a gap between these two quantities. So we obtain the theorem. That is, in this case, the entanglement manipulation is irreversible. We also give some sufficient conditions. For example, if there is a gap between the upper bound of distillable entanglement and the lower bound of entanglement cost, we can obtain the irreversibility. And applying it, we can show that for any rank 2 state supporting all this anti-symmetric space is irreversible under PPT operations. So to conclude, we first show a better upper bound than log negativity. And however, address told us this quantity actually does not improve the range bound. And the second result is that the range bound is not additive. That is, we need to consider the regularized range bound. And the second result is the lower bound for asymptotic relative entropy of entanglement. It can be also lower bound than entanglement cost. And with this lower bound, we show the gap between asymptotic relative entropy of entanglement and the asymptotic range bound. And this gap helps us solve the problem. and show the irreversibility under PPT operations. There is still some problems left. For example, we do not know whether the regularized range bound gives the PPT distillable entanglement. And we also, the lower bound E eta we obtain is not tight. And a problem is how to further improve it. And finally, since we are doing estimation of distillable entanglement and entanglement cost under PPT operations, problem is how to further evaluate it without using PPT operations. And both of the details of these results can be found on these archive papers. And I would like to thank my collaborator and supervisor Ren Yao. That's all. Thank you for your attention.
So we can take some questions. Yes.
Hi. I was wondering if you've considered generalizing sort of the class of operations that you allow from PPT to even sort of more general, I guess, like other broader class of operations that can serve as entanglement witnesses. Because I know that there's like a generalization of the Paris-Hordesky criterion that sort of applies to like all maps that are like partially positive, and you know, I was wondering if that sort of generalization is something you thought about.
Yes, thank you for the question. Actually, I didn't think about how to further generalize PPT operations. I think perhaps it is more important to study the operations between LLCC and the PPT operations. Mm-hmm. We hope to find more operations which has tractable structure to help us better study the distillable entanglement and the entanglement cost. Yeah.
Cool.
Yeah. So I have a question. When you were talking about the asymptotic range bounds,
yeah.
You mentioned that you used, your technique was semi-analytic, semi-numeric.
Yeah.
Can you go into describe that a bit more, and what ways were you using both approaches?
Okay. Wait a minute. So this is the approach. Yeah. The one copy case is analytical. The state and the closed PPT state we construct is analytical, and is given here. And the second step is numerical, but we make sure the PPT state tau here we found is very accurate. It is a PPT state, and we put it into upper bound the two-copy range bound, and then compare it.
So in what step is in the numeric step in making sure tau is PPT? Is that where you're using the numerics?
Yeah, this step using numerics, it will use algorithm developed by Grad, and it's actually this algorithm can approximately estimate the relative entropy of entanglement, and it can at least give some upper bounds. It can find some feasible solutions that is produce the PPT states.
Okay, thank you.
Do we have more questions?
Yes.
So it's a more speculative question. Do you see any possibilities of treating multipartite entanglement using these PPT operations, like tripartite entanglement?
I think in the multipartite case, the reversibility is already proved by Hirizaka and Planio in 2005. And actually, you can use PPT operations to study the multipartite case, and can obtain some results. Yeah.
More question? Okay, if no more question, let's thank the speaker again.